Okay, so we've done some practice on our notes. We found that when we draw this VF, VI, delta V triangle, and we perform the vector addition, adding VI with delta V, so that V final is the resultant, in this process, the delta V always points toward the center if you mark it from the average position. So if we go from here to here, on average, we're at the purple dot, and look at that, delta V points in toward the center. And if delta V is toward the center, so is acceleration. And we did this for 4 different examples. So what do we notice when we look at these examples? Well, when an object moves around a circle at constant speed, that's important, because the VI and the VF were the same length, the acceleration always points toward the center. Toward the center, we can mark this down, of the circle. And we already talked about what we call this acceleration, the centripetal acceleration, so we've got that. We're not going to watch this video, but you can look it up if you're interested. But the big idea, when an object moves around a circle at constant speed, the acceleration is toward the center, it accelerates toward the center, and its velocity is tangent to the circle. Okay, so when we solve problems, you might think that with forces, forces should be positive and down forces should be negative, like gravity should be negative. But that's not the case for circular motion problems. When we deal with circular motion, here's the sign convention we use. We're not using this anymore. Instead, we are going to say forces pointing into the circle are positive, and forces pointing out away from the center are negative. So let's try some practice. Okay, we're going to state the net force pointing into the center. So we've got one force here. Here we've got 2 that we need to add up. And here we've got 2. Let me try it. I'm going to make some mistakes the first time around. Okay, this is 25. It's down, so it's negative 25 newtons is the net. There are no other forces to add. Wait a second. Negative isn't down. That's pointing in toward the center of the circle. And if it points into the circle, it's a positive force. Okay, let me try the next one. This one is pointing into the circle, so it's positive. Alright, so let me do 34 plus 9. The net force is this right? Am I doing this correctly? Add them up. No, I've made a mistake. What's my mistake? Well, the 9 is out away from the middle of the circle, so I have to make it negative when I add them up. So 34 plus a negative 9 gives me a net force of 25. So that's 25 too. And the net force is positive because it's toward the center. Okay, how about here? In this case, the 55 is up, but that doesn't matter if it's up or down. The important thing is it points into the circle, so it's positive. The 7 is out away from the circle, so it's negative. When I add the positive 55 and the negative 7, what do I get? 48. And again, it comes out positive. So here are the equations for uniform circular motion. First, this word uniform means that the object has a constant speed, and the constant speed is v. The velocity, however, is not constant. Look, we did that on the last page. The velocity is always changing because the direction is always changing. So even though the speed, the arrow length, the magnitude, even though that never changes, the direction changes, and therefore the whole velocity is changing. So only the speed is constant, not the velocity. Here's how you calculate the centripetal acceleration of an object in uniform circular motion. You take the speed, you square it, and you divide by the radius of the circle. Now we can use Newton's second law, which says that the net force is equal to mass times acceleration. And we can calculate the net force on an object moving in a circle. We can call that the centripetal net force, so we could add a c here if we like. And it's m times this acceleration. In place of a, I'm going to put v squared over r. And I get mv squared over r. So our homework is going to involve some problems where we use these equations and this equation.